You've probably learned in your middle school science class that all matter in the universe is made of atoms. Atoms are made of a combination of protons and neutrons in the nucleus and electrons orbiting the nucleus, and you can mix and match these particles to create different substances with unique properties. Now that's all fine and dandy, but there are still few questions to be raised. How are protons and neutrons clumped together in the nucleus? How do atoms fuse and break apart? Are these three subatomic particles made of smaller things? And how do we explain the existence of things not made of matter, like light? Enter the Standard Model. The Standard Model of particle physics is the culmination of decades of research and experiments by physicists aiming to describe the universe at the most fundamental level. The model is categorized into three groups: quarks, leptons, and bosons. First, let's go over the quarks. There are 6 types of quarks, each in 3 pairs: up and down, charm and strange, and top and bottom. The up and down quarks, which are the most stable pair, form the protons and neutrons we all know and love, with protons having 2 up and 1 down, and neutrons having 2 down and 1 up. The other 2 quark pairs, charm and strange and top and bottom, have similar properties to up and down, but they are much heavier and contain more energy, so they often decay into up and down. Below the quarks, there's the leptons. The world-renowned electron is actually a type of lepton. The heavier muon and tau leptons are less stable and decay into electrons. These 3 leptons also have neutrino counterparts. Neutrinos, often produced by radioactive decay, are very light, and since they aren't affected by the strong interaction, which we'll get into later, they phase right through ordinary matter. Oh, and there are a lot of neutrinos. I mean, a lot. By the time I finish this sentence, several trillion neutrinos from the sun have passed through your body. The quarks and leptons I've just described are in their own group called fermions, which make up all the matter in the universe. But how do these particles interact with each other? That's where the bosons or force carriers come in. The photon carries the electromagnetic force responsible for light, radio waves, and everything else on the ER spectrum. The gluon carries the strong interaction, binding quarks together and clumping up protons and neutrons in atomic nuclei. The W and Z bosons carry the weak interaction, responsible for radioactive decay. The Higgs field, populated by the Higgs boson, gives every fundamental particle their mass. And there you have it. These particles are as simple as they get. They help explain every phenomenon and every experiment you've ever done in your science classes. Or do they? There are still some things left unexplained in this model, such as how only 5% of the whole universe is actually made of matter, but the rest made of dark matter and dark energy, as well as how only matter exists in our universe, which should have all been destroyed by antimatter during the universe's creation. The Standard Model even omits one of the most well-known forces in science: gravity. Research suggests that a graviton exists, but scientists haven't found a way to fit it into the model cleanly yet. Nevertheless, through careful testing and experimentation, the Standard Model helps us learn more about our universe, one particle at a time.